Number one, I can write and solve proportions to solve problems. Can we write proportions?
Yeah.
Can we solve them?
Yeah.
We should be able to at this point in the game. We can use proportions to identify similar polygons. We've talked about writing proportions to identify similar polygons. What do you know about the word similar? Corresponding angles are congruent, corresponding sides are proportional. Look at you guys. Use theorems involving similarity about triangles. We're going to talk about one theorem today, and then we're going to build on that. And that theorem that we're talking about today is called the AA similarity postulate. What's AA stand for? Angle, angle. Rock it, girl. We're talking about the angle-angle similarity postulate to prove that triangles are similar. Not congruent, similar. Alright, the angle-angle similarity postulate says this. If two angles of one triangle are congruent to two angles of another triangle, then the two triangles are similar. Not necessarily congruent, but they're just similar. So, here's just an example. If I tell you this is 110 degrees, and this one is 30 degrees, how big is this one?
30 degrees.
30 degrees. How big is this one?
110.
110. How big's the third angle? How do we find this third angle? How many degrees in a triangle? 180. What's 110 plus 30? 140. What's 180 minus 140? 40 degrees. So I now found that one. If this one's 40 degrees, what's this one? 40 degrees. Check that out. If I know two of them, the third ones have to be the same, and because that's true, our triangles are going to be similar. Look at this example here. It says determine whether the triangles are similar. If they are, write a similarity statement and explain your reasoning. Here I have angle C is 26 degrees. Angle D is 90 degrees. How do I find the third one? Yeah, 90 and 26 added together is 116, and subtract that from 180. 180 minus 116 gives us 64 degrees. How big is this one? 64 degrees. So 64 degrees is at angle E. So here's my question. If this one's 90 degrees and this one's 64, how big's that one have to be? We just did the math. 26. So determine whether the triangles are similar. Are they similar? Yeah. So write a similarity statement. You can do this one of two ways. You can look at it and you can tell. A lot of us would benefit from taking it and actually redrawing it. So if I take this one and redraw it to look like that one and spin it around, I have 90 degrees is letter D. 26 degrees is letter C, so it corresponds to that one. And then I have 64 degrees here, and this one was letter E. So I took this one, redrew it down here, and now I'm done with that. So what's my similarity statement look like? Triangle, however you want to name it, ECD is similar to triangle HKG. Nice job. So that if I go 64, 26, 90, I go 64, 26, and 90 again. So that E and H match up, C and K, and then D and G match up. So, one more time. Are they similar? Yes. Write your similarity statement. We did. Explain your reasoning. Ready for this? To explain it, what did we just do? What postulate did we use? We used the angle-angle postulate. We knew all the angles, so we could figure out all the angles, so how is that true? By the angle-angle postulate. Look at this one. We have triangle ABE and triangle ACD. Do you see there's two triangles in that picture? Here's this triangle. And then I have this one as well. I'm going to take them and I'm going to pull them out. Here's the big one. You should do the same. Redraw them on your paper. We have ACD. And we had 52 degrees down here. And we also have this one, which is ABE. And we have 52 degrees here. Do I know any other angles between those two triangles? What do I do? What happened here? If I pulled this one out, what do you know about this angle and this angle? Aren't those the same between those two triangles? Do you see this? Those two triangles overlap. So when I pull the one out, this angle and this angle really are the same, right? No, we don't know how big they are, but we do know that they're the same. So I'm going to put congruent marks in there to show they're the same. So if I have two angles and those two angles are the same, that's enough to tell me that yes, they are similar. So I can say yes, triangle ABE is similar to triangle ABE, ACD. Yes, they're similar. How do you know? By angle, angle. I have two angles are congruent to two angles of the other triangle. Part B. What do those arrows mean? They're parallel. So we've got parallel lines. What else do we have? Going all the way back to chapter 1, first try. What forms an X? What kind of angles form an X? Do you see vertical angles in there? So what do we know? This angle is congruent to that angle, right? You've got your vertical angles. And check this out. I'm going to extend this just so we can see this. This line and this line are parallel. And I have this line that comes through here, and I call that a transversal. So we kind of turn our head sideways a little bit. And what do I know about this angle and this angle? What are those called? Why are they congruent? What kind of angles are they? What's the name for them? Alternate interior, because they're in between. Good start, Dylan. Way to finish it up, Mason. So I've got that line there, and now what happens if I go like this? I'm going to erase this a little bit. Get these other lines out of here. What if I draw the line this way now? I've got this line here, my parallel lines. We also have alternate interior angles that way, right? You see those alternate interior angles? So, what did we just do? I've got three sets of congruent angles. Are they similar? Yeah. So, I wrote all over this now, but this was a T. So name it. If I go 1, 2, 3, I have VSR. Triangle VSR from 1 to 2 to 3 marks is similar to triangle 1 to 2 to 3. VUT. Explain it. Why are they similar? By angle, angle. That's all we're dealing with is angles in these triangles. How about here? Raise your hand and tell me, in number 1, what kind of triangles are those? Raise your hand and tell me. What kind of triangles are those? Just wait till I call on you. But yes, they're equiangular. And if they're equiangular, they're also equilateral. And if they're equiangular and equilateral, we say they are regular. Regular. Remember that equilateral and equiangular means they are regular. So, what do I know about this? How big are each of those angles? 60. 60 degrees, 60 degrees, 60 degrees. How about on this one? Oh, they're all still 60. Are they similar? Yes. By angle, angle. And so if I say write a similarity statement, this is kind of they're throwing you for a loop on this one. What parts are congruent to each other? Isn't this one congruent to that one? Isn't this one congruent to that one? Isn't this one congruent to that one? Yeah, so in this case, it doesn't matter which letter you start with and which ones you match up because they're all equal to each other. This is the only time this is going to happen though. So we have triangle FGH, I might just say, is similar to, and just for the sake of consistency, because this is what we always do, if I have FGH, I'm going to start here and I'm just going to say QRS. Those are similar. But again, it doesn't matter because in this case, they're all equal to each other. Number 2. We have 32 degrees, we have 90 degrees, and how do I find this one? How many degrees in a triangle? 180, so what do we do? Yeah, add 90 and 32. Gives us 122, 180 minus 122 gives us 58 degrees. So this angle right here is 58 degrees, right? So now over here, all I have is a 58 degree angle. Do I know anything else about this triangle? We know this side over here is also 90 degrees at vertex F. So if I have a 90 and a 58, and 90 and 58, the third one has to be the same. Do the math, 90 plus 58, subtract from 180, you're going to get 32. So, are they similar? Yes. How do we know? It's angle, angle. And here, we have to go in now and write your similarity statement. If I were you, I'd take one of these triangles and redraw it so it looks like the other one. If I take this one and turn it, doesn't matter which one you take and turn, as long as you do it. We've got a 90 degree angle, which is at F. 58 degrees is at E. And 32 degrees is D. And this is my D. I took that one and I redrew it, now I'm done with it. So what's our similarity statement look like? Okay, triangle DEF is similar to CDF. Some of you may have not started at D. You may have said triangle EFD is similar to DFC. The part that is the most important is that D and E have to match up, F and F have to match up, and C and D have to match up. So when you write your letters, they have to match. You guys know that, but just don't forget that. Number 3 says, suppose in example 2, this question on the previous page, I'll get there in a second. If the lines are not parallel, can the triangles still be similar? If these lines are not parallel, are we going to have congruent angles in there? No. The only time we can say we have alternate interior angles that are congruent is if the lines are parallel. Nice job, Dylan. How about this one? A flagpole casts a shadow that's 50 feet long. We have 50 feet is the shadow. A woman standing nearby is 5 feet 4 inches tall. My lady is 5 foot 4 inches. And the shadow is 40 inches. Her shadow is 40 inches. I want to know how tall is my flagpole, so I'm going to call it X. So if I want to solve for the height of the flagpole, my first concern is this. I look at that problem, and what makes you a little hesitant right away? What do you notice about that problem, the way it's set up? Raise your hand and tell me what's wrong. We've got different units. If I try and take 40 inches and turn it into feet, is it going to come out nice? If I go 40 divided by 12, it's going to give me some kind of decimal. So here's what I'd like to do. I know that 1 foot is 12 inches. 2 foot is another 12 inches. 3 foot's another 12 inches. How am I going to turn 50 feet into inches? Times it by 12. I have 50 12 inches. 50 sets 12 inches, right? So if I multiply, that gives me 600 inches is the length of that shadow on the flagpole. 5 feet 4 inches. Can I take this 5 feet and turn it into inches here? Same thing. If I have 5 12 inches, 5 times 12 gives us 60 inches, but she was also 4 inches on top of that, 5 feet 4 inches. So 60 plus 4 gives us 64 inches is the height of our lady, right? Now I have inches and inches and inches. It's all in the same units. How am I going to solve for the height of the flagpole? What am I going to compare? What corresponds? So how am I going to set up my proportion? What's the height of the flagpole compared to? The height of my flagpole compares to the height of my lady, which was 64 inches. Do you see what I did? X over 64, my lady. And then I have the shadow over the shadow. 600 over 40. Draw in your arrows and be consistent. If I go flagpole to lady, I go flagpole to the lady again. Oh, we can do that. I like that. Brent looks at this, he's like, hey, Mr. Those zeros cancel. I can simplify that so that the mental math becomes a little bit easier. Sure. You don't have to, but sure. So now it looks like this. X over 64 equals 60 over 4. We cross multiply. 4 times x is 4x. 60 times 64. That's still a big number. X equals 960, but all those were in inches, right? So I'm still at 960 inches. So now if I have 960 inches and I want to divide them into 12 inches, how many feet is that? Gives us 80, and 80 is feet. Yeah, look at that.